Good morning. We will start with the boiling curve. We had left with a brief introduction to boiling heat transfer in the last module, and what was seen was why flow and pool boiling, which are two broad classifications of boiling heat transfer, need to be studied. And we made one statement that the heat transfer coefficient which one sees in flow boiling is much greater than what is seen in pool boiling. What is heat transfer coefficient? The definition of heat transfer coefficient and other quantities that were studied remain the same in case of boiling heat transfer also. That is, if we go back to our fundamental definition of Nusselt number, Nusselt number is seen to be a function of Reynolds and Prandtl number for forced convection. And in flow boiling also, apart from these two non-dimensional quantities, you would have several other quantities which are going to be there. So, there is a flow aspect, there is the nature of the fluid, the Prandtl number aspect, and other quantities which are important from boiling point of view. Those quantities would also occur in the expression for Nusselt number. In single phase heat transfer, we had correlations which looked quite nice to see and use. For example, your Dittus-Boelter correlation, which was 0.023 Re to the power 0.8 Pr to the power n, and it was quite easy that one could do a problem using paper and pen quite easily using this Dittus-Boelter correlation. However, in case of boiling heat transfer, you would have correlations which are quite elaborate. Why? Because unlike single phase, where there is just plain flow and single phase heat transfer sensible heating, here you have various changes that are happening in the flow. And to make the long story short in view of time, I just want to give a couple of examples. So, when you talk about simple air water kind of flow, like you've gone out of town and the water tap is not being used for a long time, you have a plastic hose pipe. Hose pipe is the pipe which is used to connect to a tap, and you can use it to garden, to water the garden, etc. So, if the pipe is transparent and the tap has not been used for a long time, the water pipeline has a lot of air in it. When you open the tap, you initially see you initially have a whistling sound of air coming out, and then there is water coming along with air, and then after a few seconds you have complete water flow. And I am sure all of us have noticed the way water and air come out is very different when the pipe is held vertical, when the pipe is inclined, when the pipe is horizontal. Well, the hose pipe, if it is transparent, you will start to see various kinds of orientation of the air and water. For example, if the pipe is horizontal, you would sometimes see air like this and water flowing this way. You probably would have seen couple of bubbles there before, and then this way, and eventually you would get completely liquid flow. If the hose pipe was held vertical, you might even see some large chunk of air which is here, and then liquid here. You would see another bubble here and the liquid flowing this way. So, or if it was inclined, you would probably see something like this. This is air and this is water. So, what we are trying to say is that it is the same tap, it is the same pipe of the diameter, same material, but the nature of the flow here is very different from here. Why? Because remember, in single phase fluid mechanics, we had this concept of wall shear stress, which is nothing but something given by mu du by dy, gradient of the velocity at the wall times the fluid viscosity. Now, if you are talking of fluid viscosity, we all know that liquid as well as vapor have different viscosities. What I am showing for air water can be directly extrapolated to steam water or any substance and its vapor, or a mixture of substances which are in different phases. So, air water is a simple example. We can also use this for steam water situations. The point being, the viscosities and the densities of the vapor phase are very different from the viscosity and the density of the gas phase. Liquid phase, mu g, rho g, these are going to be greatly different. And because they are greatly different, how they interact with the solid surface, the wall shear stress when liquid is in contact with the wall is very different from the wall shear stress when vapor is in contact. And this gives rise to different wall shear stresses. T wall with liquid, T wall with gas is not the same. For example, if I have a circular pipe and it is exactly filled with liquid at the bottom half and vapor or air, or if this is water and this is steam, let me call this G, steam, exactly through center you have the interface. The wall shear stress here versus the wall shear stress in this half is going to be greatly different because the viscosities are different. And same thing, because the specific volume or the density of the vapor phase is very different from the liquid phase, the inertia effect for these two phases are going to be different, and therefore you would know that you have observed also that the vapor or the gas phase is seen to go faster, much faster compared to the liquid phase. The liquid will occupy much lesser space compared to the vapor. Therefore, even if a small amount of liquid gets converted to vapor, it is going to occupy much larger space than the equivalent amount of liquid. And because in most industrial applications, in real life application, the flow area is kind of fixed. Suppose it is a circular pipe and this was, you had completely liquid here. At the next time t plus delta t, a small amount of liquid has gotten converted to vapor. This is liquid and this is vapor. This vapor phase is going to occupy a certain amount of space. The next stage, when little bit more vapor is generated, you would see that vapor is occupying much larger amount of space. Though in terms of thermodynamic quality, you would go from x is equal to 0 to x is equal to say 0.02 or something like that only. So, very small changes, dx is very small, very small changes can give rise to very large changes in the volumetric flow distribution. And therefore, in two-phase flow, in addition to quality, we have a quantity called void fraction or alpha, which is very important. Void fraction or alpha refers to, it is actually a triple integral, because this is the distribution of vapor phase and liquid phase is going to be a function of space and time. But for all practical purposes, we would say the definition for alpha or void fraction is nothing but integral, triple integral dVg over V total. Okay. This can be translated very easily to Vg over Vf plus Vg. So, how much fraction of the space is occupied by the vapor phase to the total volume in a given control volume. It is a very important definition. Why? Because if I write this in terms of the flow area for a given delta z of the control volume. So, if this is a control volume of thickness delta z, and in this, please imagine this in 3 dimension, there are chunks of vapor which is present here, extending here, etc. The control volume can be given as Ag delta z divided by Ag plus A liquid, and this could in turn become the definition of the void fraction. A very important fundamental quantity in two-phase flow is this void fraction, and I will just show you very quickly how and why this is so important. Okay. So, we have thermodynamic quality. There are of course 3 definitions of thermodynamic of quality here in two-phase flow. I will not go into the details. This is the common conventional definition. This is m dot g plus m dot f, and this is written as rho g Ag Ug divided by rho g Ag Ug plus rho f Af Uf. If I divide through by the numerator, I would get 1 over 1 plus rho f by rho g, af by ag, uf by ug. Okay. Now, let me just write it in a slightly better way. 1 over 1 plus rho f by rho g, we can retain it as it is, ratio of the properties. Uf by ug is nothing but the velocity of the liquid phase divided by the velocity of the vapor phase. And if I go back to this definition of void fraction, alpha is equal to ag by ag plus af. 1 minus alpha is af by ag plus af, correct? I use this definition here, these two would go in here and I would get this as 1 minus alpha divided by alpha. So, my definition of thermodynamic quality is nothing but this very important relationship. And where two-phase flow becomes so complicated compared to single-phase flow is that the density is probably, yes, if I assume equilibrium, I can say that the densities can be known. I said the speed or the velocity of the gas phase is going to be much larger compared to the velocity of the liquid phase. So, this quantity ratio is called 1 over slip. Slip is S is nothing but Ug by Uf. This quantity is essentially unknown. So, I will write this again here. So, slip ratio is Ug over Uf, which is always greater or at best equal to 1, always greater at best equal to 1, and therefore, x is nothing but 1 over 1 plus rho f by rho g into 1 over slip ratio 1 minus alpha by alpha. Now, what makes two-phase flow so difficult is the fact that I do not know what the slip ratio is. I do not know what the individual velocities of the two phases are. When I am trying to sip a cool drink through a straw, the air bubbles in the cool drink and the cool drink come into your mouth at the same time. So, in that case, the gas phase and the liquid phase are traveling with the same velocity, in which case slip is equal to 1. But in most situations, that is not the case. Also, void fraction, what is the volume occupied by the vapor phase and the liquid phase, that is also not known. In addition to this, if I keep a pipe which is oriented this way and exactly the same amount of liquid has gotten converted to steam, for example, I have a heat exchanger which is oriented horizontally, a heat exchanger which is oriented vertically. Okay, and I have a change in quality from, say, x is equal to 0.3 to x2 is equal to 0.35, x1 is 0.3, x2 is 0.35, same number change, x2 is 0.35 and delta x is 0.05, delta x is 0.05. How these two phases, how the liquid, water and the steam are going to orient itself in these two arrangements is going to be very, very different. Why? Because here I would have gas or vapor accumulating at the top and this is liquid. Because density is less, liquid tends to move to the top, the gravity is going to act this way. Whereas in this case, you would have the flow this way, liquid is here and the vapor is flowing through the center. Most often this would be the flow pattern. And for the same diameter pipe, if this is the same D here, in horizontal case, I can clearly see that the surface area, if I take a view, cut section view here, this is your vapor phase. If I take a cut section view here, vapor is in the center. What is in contact with the wall? Liquid is in contact with the wall. Here liquid is in contact with the wall only for this portion, whereas at the top you have vapor in contact. So, why I am trying to tell all this is shear stress at the wall in this case and shear stress at the wall in this case, vertical, horizontal, very, very different. Now, let us go to heat transfer coefficient. Heat transfer coefficient is minus k dt by dy at the wall. divided by some delta T reference, right. This was our definition. So, if I have liquid in contact with the wall versus gas in contact with the wall, the gradient associated is going to be different. The thermal conductivity of the liquid would be different from the thermal conductivity of vapor. Therefore, heat transfer coefficient when I have liquid in contact versus vapor in contact is going to be different. And mind you, both the problems are the same, change in quality because of, if I go back to my equation from the previous module, change in quality is directly related to the heat flux. So, heat flux would have been the same, all these things here would have been the same, the change in quality is the same. What has changed is the orientation of the pipe. The pipe was initially horizontal and you got a distribution like this. Another experiment, the pipe is vertical, you get a distribution like this. The characteristics associated with the flow are going to be greatly different, and therefore orientation of the flow becomes very, very important, and that is why two-phase flow becomes very complicated. Okay, these are things which you would not get to see in a textbook per se, because in an introductory heat transfer course where boiling curve is curved, this much of explanation is rarely given. But I am just telling you because it is not a very, very simple simplified analysis that you can do as you did in a single phase flow. So, if I go back to my set of slides here, yeah, Nusselt number is going to be a function of Reynolds Prandtl number, also the flow pattern or flow regime, which is a function of the geometry and the orientation, nature of boiling pool or flow, external or internal. This is of course going to be there if you are going to have boiling inside a tube versus boiling on a surface, but most engineering applications we are going to consider boiling over inside a tube, and mechanism of phase change, which is nucleation or evaporation, or condensation, which is film or drop. We are going to restrict ourselves to boiling, which is nucleation type. Now, what is this boiling curve? Boiling curve typically is a graphical representation of the heat transfer processes that is going to occur, or basically you are going to have a very nice two-dimensional representation of the processes. So, the x-axis and the y-axis are going to be labeled this way. This is the wall superheat, T wall minus T sat on the x-axis, and wall heat flux on the y-axis. This is typically a log-log plot. Okay. This boiling curve is nothing but a two-dimensional graphical representation. So, what it does is it splits this area. Any graph, it's going to split the area into a portion which is above this or below this line, above this curve or below this curve. Similarly, boiling curve is going to give you the heat transfer coefficient graphically. It's a representation of the heat transfer coefficient, and it splits the region into various useful important regions. And I am just written these down here in the slides. I will come back to that one by one. Let us just take a look at the boiling curve on the slide here. Boiling curve, as you can see, its y-axis is heat flux, x-axis is wall superheat. You have what we have drawn, a curve which is red in color, A to B to C, and then there is a dashed line which goes like a U and all the way up to point E. There is some point D in the bottom, which is called as some Leidenfrost point. So, this is what you see in the textbooks as a boiling curve, or some variation of it. The curve would be similar. You might not have this much of naming like natural convection, partial nucleate boiling, fully developed nucleate boiling, transition boiling and film boiling. These are specific regimes that you see. A typical boiling curve would look like this. How does one obtain this, and what do each of these regions mean? So, for this we have to do a simple thought experiment, and let us get back to what we have been doing here. The thought experiment is very, very straightforward. It is basically you are trying to generate heat transfer data, heat flux versus wall superheat, T wall minus T sat. This is called as wall superheat. Now, I can have two different types of experiments that I can do as a scientist. One is heat flux controlled. The other is wall temperature controlled. What does this mean? Is that I will control the heat flux. This doesn't mean heat flux is constant. I will ramp it up to a value Q1, keep it constant. Then next time I will make it Q2, keep it constant, allow it to reach steady state. So I am controlling heat flux and nothing else I am able to control. The other one is where wall temperature is held constant, T1, TW1 value. Then next I would go to TW2, TW3. I am going to control this. And these two situations give rise to different nature of the boiling curve. What you see in the textbook is a combination of these two boiling curves. You don't get both, you don't get this kind of boiling curve that was shown for either of these. What is shown in the textbook is a combination boiling curve which takes care of both heat flux as well as wall temperature control cases. Please remember, we are talking about control of the heat flux as an independent variable. That means I have a rheostat with which I can increase the voltage or the current and increase the heat flux. Keep it constant, allow it to reach steady state, note down the readings, then increase the value a little bit more. This is what is heat flux control. Wall temperature controlled is where I control the wall temperature. The wall temperature would have been 60, then goes up to 65, goes up to 70. How I control, what is the mechanism by which I am controlling, that is not of concern to me. All I want to know is the wall temperature controlled by me, and is it being able to, am I able to hold it constant for certain amount of time so that a steady state is reached. Obviously, wall temperature control experiments are a little bit more difficult to do. Nevertheless, they are done. You have some kind of a condensation or a boiling of another fluid happening on the other side of the surface over which you want to study this boiling curve. So, you keep the surface at a particular temperature by boiling or condensing some kind of liquid. Now, heat flux control, let us try to do. What you do is, I have, and this is studied in a pool. Okay, pool boiling curve is what you would see in most textbooks. This is typically called as pool boiling curve. You would not see any curve labeled as flow boiling curve. Why? That also I will tell you at the end of this session, is because we said that pool boiling and flow boiling curves are essentially nothing but very different, except the heat transfer coefficient in flow boiling is slightly higher. Why it is higher, that also we will see. So, if I have a particular pool, that means stagnant water here, okay, and I am trying to heat this either by external means or have a wire coil through which heat is being supplied. Whatever be the way, there is either Q coming in this way, or Q could be coming in because of some coil, which was what was done by Nukiyama. For the first time, he studied the boiling process and generated this boiling curve. That is why it is called as Nukiyama curve also. So, you have some means where heat is supplied, and this pool was initially at some temperature T infinity. Okay. So, what happens is what we do for boiling water for tea also, you have a stagnant pool and you slowly start increasing the heat flux. Initially, for a reasonable amount of time, the primary mechanism of heat transfer is what we call as single phase natural convection. This is what will be the mechanism, natural convection, and that too single phase. What do I mean by that? I have a high temperature here, so the fluid here becomes hot, the fluid at the top is cold, so the density here is slightly lower. So, this is going to rise up, generate currents, and this will, the hot fluid will rise up, the cold fluid will come down, and this is how the heat is going to get distributed in this pool. Eventually, entire pool will be slightly hotter than what it was before. Supply more heat, still the wall will be hotter. So, what was T infinity or T bulk mean? Let us use Tm at time T1 is now going to be Tm2 at time T2, Tm3 at time T3, and this kind of circulation will keep happening. This is called as natural convection. Why? Density difference, there is no force flow. Density difference drives the heat transfer, and what you have seen in single phase flow, a heat transfer coefficient is nothing but Nusselt number, which is nothing but minus k dt by dy divided by some delta T, and natural convection we know has lower heat transfer coefficients. So, you will get typically a very low heat transfer coefficient in this case, and this process of natural convection will continue until the process of boiling starts. And where and when does this process of boiling start? When I take the surface and I zoom into it, the wall temperature, as heat flux is increased, wall temperature also starts to increase. Wall temperature starts to increase as Q double prime increases. So, I go on from Q1, Q2, Q3, I go and set a value some QW, where the wall temperature now is say, and you are doing with water at 1 atmospheric pressure. What is the boiling point or saturation temperature? T sat is 100 degrees centigrade for water, and when the wall temperature reaches near 100 degree, we start to become a little bit anxious of what is going to happen, and the boiling process starts when the first layer of fluid, I am giving a small gap, when the first layer of fluid in contact with the wall reaches to a temperature slightly greater than T wall greater than T sat, which is 100 degrees centigrade. So, when the wall temperature reaches 100, the layer in contact with the wall will also be 100 because of no thermal slip, and when the temperature of the wall becomes slightly greater, that how much slightly greater we do not know, but when it is slightly greater, say 101, 102, first action in terms of boiling will start. This and more next module. Thank you.